Okay, hello everyone. I'm Sansar Raj Meena. I'm working as an assistant professor at the University of Padua in Italy. And currently I'm a visiting researcher at the University of Twente. Today I'm going to talk about deep learning for automated landslide mapping. And I will be assisted by my colleague Kushanav Bhuya. He's a PhD student in our research group in Padua. So let me introduce myself. I'm more about my work and what I studied in the past. So I did my bachelor's from University of Delhi in geography honors. Then I went to Netherlands and did my master's in GIS and remote sensing, focusing on
Sansar, sorry, you're muted again for some reason. I think there's an issue with Microsoft Teams today, so we'll have to keep a check on the muted problem.
Can you hear me now?
Yeah, now it's fine. Yeah.
Yes, okay.
I'll let you know if
Yes, we can hear you.
Okay.
Again you muted, sir. Again you muted. Please unmute that.
Now
it's okay now. It's okay now.
Now it's fine. Okay, then I have to do it like this. Or because if I click presentation mode, not muted, right? Can you hear me?
Yep.
Okay, good. So I was saying I did my bachelor's from India and then I did master's from ITC with working with Case One Western. Then I went to Austria. I was working there with Professor Thomas Blaske. And then last year I came to Padua. I work as a postdoctoral researcher. And this year at the start of January, I joined STEAM, Machine Intelligence and Slope Stability Laboratory. There I'm working with Professor Filippo Catani and Professor Mario Flores. And then today, I will share the half part of the lecture with Kushnav Bhuya. So the overview of today's lecture is we divide the lecture into two parts. So I will just talk for 30 minutes, give you an overview about artificial intelligence, what is deep learning, and how we can use it for landslide detection mainly. And the second part is around 50 to 60 minutes, and it will be more hands-on session, which we will give you a demo in Google Colab. And there is also instruction manual that you can find in the Google Drive folder, which you can also follow later. So let's start with the introduction to artificial intelligence. So let's start with intelligence first to understand what is intelligence. Intelligence is an ability by which we can take some information and make some decisions based on that information. And then from that artificial intelligence came, and then artificial intelligence is an ability for computer. We teach a computer to take information and use that information to make decisions. And then machine learning is a subset of artificial intelligence in which we focus on teaching the machine how to learn and machine to learn from experiences, how to learn from data without explicitly programming it. And then we move to deep learning more recently after 2010, as you can see in this figure. So in deep learning is also a subset of machine learning and AI, in which we focus on use of neural networks to automatically extract information or features from raw data and use those patterns or features to inform learning tasks and make decisions. So let's move to the next slide. So trends in somebody's mic is on. Can you please turn it off? Trends in AI. So now, why we want to use deep learning? You know, why what is going on at the moment? So you see the deep learning or with the machine learning, we have unprecedented results in a speech variety of fields: speech recognition, computer vision, time series forecasting for many tasks. And then now, you know, before for these concepts are already there. They were there for decades, but now we have more capabilities of GPU, graphical processing units, more big data sets now. Data are everywhere, and also open source TensorFlow libraries by Google are available. And now this is some applications of AI domain. There are many applications, many domains in which we can use AI, like optical character recognition, speech recognition, in search engines like in Google, how they index the searches. And also, if you see, you talk about something like buying an iPhone, then you see an ad on your phone about iPhone in while you are browsing internet. So, and also autonomous driving. And today we are going to focus on remote sensing. So this is an example in this image where we can use AI to classify an image and try to identify the objects. This is just an example of image classification. And then this is an example of recently developed dynamic world near real-time global land use or land cover mapping, which was developed by people by Brown et al. And this is a published research, and now it's freely available in Google Earth Engine. So these are some of the examples in remote sensing. And we want to understand how we can use AI in remote sensing and why, because you see, this is an example of large or vast variety of sensors which are available, which are freely. For example, this image I took because we can get this open access data, Landsat, MODIS, Sentinel, Sentinel-2 now, and the data are vastly available. They are big data now, and we can use these for making our decisions for remote sensing derived from remote sensing images. This is another example where if we can look on different spatial resolutions like Landsat, like Sentinel 10 meters, more recently for research Planet Scope or Rapid Eye data is available through, you have to ask them for research purposes, which have a spatial resolution of 5 and 3 meters. And then there are vast variety of spectral resolution data available. So we now have to understand, okay, how we can use this kind of data in remote sensing. So moving forward, these are applications of AI in remote sensing. Moving forward, I want to give an overview of machine learning. So before moving ahead, I want to give you an overview of what is learning and inference. You know, there are two types of learning: supervised learning, in which we give a training data set is available. You know, we give an input. For example, I give you always today an example of landslide for only because the lecture is about landslide. So we give the model labels about if there is a landslides or not, or non-landslides. This is supervised learning. Unsupervised learning, where we don't give the labels at all to the model, and then it has to think and differentiate between the labels itself. And there is the third one is inference, in which we don't give anything to the model at all, and then train the model somewhere in some location, and then try to test it or inference it in a completely unseen data set. Moving ahead, this is an example of machine learning application. Is a work, you can say a workflow, like we have classification of remote sensing images. So first we do pre-processing, then feature extraction or selection and classification. And then we get an output, in this example, a landslide. So here we get if there is a like landslide or no. For this is just an example. And then in deep learning, moving ahead with deep learning, this is again a field that gives computers the ability to learn without being programmed or giving any input from ourselves. And then there are this is a subset, as I told already, of artificial intelligence and machine learning, and there are a lot of related fields like computational statistics, pattern recognition, data mining, computer vision. So just to understand what is the difference between machine learning and deep learning. So the main difference is that in machine learning we use feature extraction. We do feature. There is a flow, like we give input, then feature extraction, then classification, and then it gives you an output. But in deep learning, feature extraction and classification are done within the model. These are the main differences in machine learning and deep learning. And then before going ahead and to show you more application of Landslide, I want to give you very basic overview of what neural networks are, because this class is not about basic or fundamentals of deep learning, but I want to give you more overview about how we can use this technology for landslide detection, which I will show you later. So first I want to explain you the elements of neural networks. The neural networks consists of hidden layers with neurons, and a single neuron map is a set of inputs into an output number. For example, we give a neural network an input, then we assign some weights to them, and then we have to add bias to it, and then there is an activation function which decides if a neuron should be activated or not, and then we have an output. And this workflow is mathematically written in the equation over here. So we have to understand that activation function plays a very important role in our output, because this decides if a neuron should be activated or not. There are many types of activation functions in the literature. This is a very common activation function, sigmoid function, and about this you will know more about them in the tutorial. And then this is I want to give you an example of how or about a neural network with one hidden layer and output, just for you to understand how these things works. So we always have to assign weights and biases, and add a bias and then activation function. This is just to show you how it works within one hidden layer, because in previous one there was no hidden layer. And this is an link, an example which I wanted to give to you, so that you can play with it and try to understand how these things work. So if you click on that link, you will come up with here. And this is just to visualize for yourself, try to understand, like we give an input, you can play with the data, like training data sets, how much you want to put, like 30% of test, and then best sizes, you can play with learning rates, regularizations, activation functions that I just showed you, like ReLU, ANHA, sigmoid, linear. You can choose them and play with them. You can choose the problem, classification, or degradation. Let's play with this with the 4 neurons, and you will see a test loss. Like you can see how these will improve if we add one more hidden layer, and you can play with this. This is like you can add as much as of you like in normal when we do detection of landslides, we have a lot of input layers, we have a lot of hidden layers, and this you will see in the upcoming slides. So moving on from here, the main topic that we want to cover is landslide detection. So just to give you an overview, what is computer vision task? Computer vision has been the primary area of interest for machine learning. So there are basically 4 types of computer vision tasks. One is classification. So we want to know if it is like this is an example of some animals. cat, and if you want to know localization, so it gives you a bounding box localization, and then there is object detection. So there are some cats, dog, and duck. So it tell you what they are and also gives you a bounding box. But instance segmentation is it tells you what they are, but also draw boundaries around them, or to, like, for example, what we are going to do for landslides. And just to point out that in most of the literature, there is a confusion between object detection and segmentation. Often people do, sometimes they do detection, object segmentation, but they call it detection. But there are a variety of synonyms for that, these used in the literature. Moving ahead, I want to just give you an example of how the features are extracted in deep learning image analysis. So just for us to understand, if we want to try to draw these faces by ourselves by hand, it takes a lot of time and then effort, and then very difficult to extract. But in machine learning, in deep learning or machine learning, we can try to teach the model to drive these features, like low-level features, like edges, and then the model learned from these low-level features, then it moved to mid-level features. So then it teaches this, then combine these mid-level features and move ahead to the high-level features, which are faced in this example. So, and I'm going to show you a lot of examples of CNNs for landslide detection. So just to give you an overview about this is this is just an example of how CNNs works. And CNNs were mainly designed for image data. And then CNNs use convolutional operator for extracting data features. They allow parameter sharing. They are very efficient to train and have less parameters than neural networks with fully connected layers like UNet. And they are also robust to spatial translations of objects in images. And the figure that is here is just to make you understand that in this case, you see an example of how you use an arbitrary convolutional filter over an input matrix, which is an image. And then you get as an output a new feature map, which carries a low level information. And then in each with each convolution filter, you transfer the information from low level features to mid level and then high level features. So this is an example of image segmentation overview of CNNs. And in CNNs, we have to understand that we can extract this information we can do this feature learning and classification in CNNs in the module itself, and then it gives you an output. And it learns these hierarchical spatial features. And this is true because the fact that feature learning and these classifications these are single component here, which can be learned from the input remote sensing image or remote sensing image. Now I move to this. That was an overview of deep learning in general, in AI, in remote sensing. Now I'm going to focus on landslide specific problems. As you know from yesterday, Hakan gave a presentation about the problems of landslides around the world, the global inventories. So this is just an example of how vastly spread landslides the problem are in most of the mountain belts around the world. You can see this in this figure. And there is another example from NASA Earth Observatory where you see the fatalities by landslides in the past years. And then moving ahead, we want to understand what in this lecture, we want to focus on inventory. So we want to understand how they are mapped, how they are done. Some inventories are done point-based, some are polygon-based, some are very specific, site-specific studies where we make very concentrated field-based surveys. But what we do if there is an triggering events such as earthquake, rainfall, or storm surge, or snow melt, or or any other triggering events. There are many, there are thousands of landslides, and if we want to map them, it's very difficult to do them manually and takes a lot of time. So moving ahead, we also want to know and understand why these inventories are important. Why in the first place we do these inventories. So we have to keep in mind that landslide inventories are very essential for landslide susceptibility, hazard, and risk studies. So if there is no landslides, background information, you don't get the information about the history of landslides in that particular area. So we need to know where the landslide happened and how many in numbers of in the number, and also if possible in terms of area and volume. And then just a very important point, another important point is we need these inventories also to train our machine learning or deep learning models. These and also to validate landslide susceptibility, hazard, and risk maps. This is an example of what is the problem in landslide mapping. These are inventories done by experts. So you can see there is a difference in number of landslides, their area. This is the problem of amalgamation. So somebody think, okay, why I should map them individually? Let's make one polygon instead of making it 5. So these are very expert dependent inventories. If you do it manually, it takes a lot of time and effort, imagery, and then a lot of things. So to counter this or to make it faster, even just after an event. So this is an example of a study that we did in 2019, which I was involved. There was, as you know, some of you may know that there was an earthquake event in 2015 in Gorkha, and then it led to thousands of landslides. And then in literature, there are differences in the landslide that occurred. So they're like from 4,000 to 25,000. Some people mapped more, some people mapped less. So that is the problem of doing manual inventories. But we try to employ different machine learning, deep learning models to understand how we can use them for landslide detection in this particular case, and also to understand what we should, how many convolution layers we should use, how much should be the layer depth, what should be the pixel, the patch size of the patch sizes, and also how which layers are important, like spectral information or topographical information, something some information like that. So in this case we use rapid eye imagery, which is 5-meter resolution, and we mapped landslides in this area. So this is just an example of initial study that we did using CNNs in 2019 on satellite image for large area. Then moving ahead, there is another study that we did to try to understand if we can apply same models or methodology in different environment and using very high resolution UAV data. In this, we use several expert-based inventories and try to evaluate them and find optimal inventory for training or testing the models. And here we just use, as you can see, can you see the cursor? If yes, then there is a RGB and slope. So we just use RGB, which are optical bands, and slope, which is also derived from the UAV, to map landslides. And we were able to test different patch sizes and also different input from the inventories. And because these were two different areas, completely two different areas, we trained the model here and test in different areas. We were able to get a very good results. As you can see, more than 80% of F1 score. And we were able to remove false positives from road, agriculture land, river beds, or near to the areas which had similar spectral signatures. And then there is another example of work that we did. As you can see, these slides that I'm showing you are how we evolve in landslide detection through the years. So in this study, we try to understand how we can use different optical data like NDVI, which is derivative of from optical data, also topographical data like aspect, curvatures, elevation, slope, and try to understand the impact of them individually and also all together on landslide detection in an area which was affected by Gorkha earthquake. So as you can see, again, we found out that slope layer was the most effective if you use just slope with optical data. Along with optical just slope layer, it can give you not a lot different results, but much better results than using everything together. And this was also done in 2021. And then after that, there has been a lot of progress in landslide detection. I'm just going to show you another example where we try to employ CNNs in a completely different area, which was affected by rainfall, heavy rainfall event in Western Ghats in India. There, the landslides are different. They are more elongated, like debris flow type of landslides. And there we tried our model to map landslides, and then we were able to map them more effectively. But then now I'm going to show you more advancement in landslide detection or landslide identification, classification through time in other literatures also, because then we will give you more time on teaching you how to do it yourself with more advanced, like the most advanced model that we have and also the data. So this is an example of landslide detection or classification from non-nadir images, which are crowdsourced images. This was published in Landslide Journal by Professor Filippo Cottani last year. And then this is another example of how we can use crowdsource information that is available in internet to try to teach deep learning models to classify from an image if there is a landslides or not. Moving ahead, another example recently is a landslide for sense dataset, which was developed by one of my former colleague from University of Salzburg. Now he's in Vienna. So they developed this landslide for sense datasets in 4 study areas in Asia, in India, in Nepal, in I think it's Western county in Taiwan, and also in Japan. So they use 70% of this, 70% of the total data set for training and 30% for testing. They use open source Sentinel data sets and
I think you're muted again, Sansar.
No voice coming, sir. Hello, sir.
Sansar, I think you're muted again.
Hello, sir.
The microphone is off.
No voice.
Can you hear me now?
Yeah, now it's
Yes.
okay.
Can you hear me?
Yes.
Yes.
Yeah,
Okay.
yeah.
Okay. Let's continue. Okay, this is another example of a study done by our colleague Lorenzo Nava here at University of Padua. This is just an example of how we can use SAR data if there are cloudy images after a significant disaster event. Then here he used VV amplitude pre and post from Sentinel-1 SAR data, and also coupled it with the slope data from I think from Alos Pulsar. I have to check. And then he was successful in even segmenting the landslides by using only the SAR data. So he didn't use optical images. So some of you will say, okay, it is a very easy area with vegetation and also landslide features clearly identified. But this is just one of the first studies that has been done in this field. So these are ongoing research which can yield in better, at least trigger more research in landslide domain in terms of landslide detection and mapping inventories after hazards. And this is an example of inferencing or testing that we did. We trained the model unit. This you can see an example of a unit model that we used and trained it in Western Ghats, which is a rainfall induced rainfall triggered landslide area. And then we tested it in Japan, which is completely different and earthquake induced, and we were able to do it. But this was a small project. And then from this, we were able to do and make more global scale landslide database, which is completely made from high resolution planet scope images, which are 3 meter in spatial resolution. So the training data set that we have, they are trained on 3 meter spatial resolution. And here we use 5 rainfall induced and 5 earthquake induced landslide inventories, which were completely made by us and tested individually for quality and completeness levels by our team in University of Padua. So this is an example of the semantic representation of the data set itself. So HRGLDD, it means high resolution global landslide data set. This is a training data set, which is 60% of the total data. We used 20% for testing and validation and 20% for testing our models. And then from the model weights, we were able to test them on individual inventories that we have. And also we tested or inferenced them directly on Haiti and Indonesia, which were the most recent events that we had at that time. And we just downloaded the planet images for these events and were able to map landslides using state-of-the-art deep learning models. And this is an example of Indonesia, where we were able to map landslides on completely unseen data. And then for the other part of it, you are going to do it in Haiti during the tutorial. So moving ahead, now I going to explain you a little bit about this code manual that you will find it in the Google Drive. This will be led by Kushana Bhuya. So for this, you need, if you want to do it, this tutorial that we are going to give, if you want to follow it on your own machine, you need TensorFlow. Otherwise, you can use Google Colab, and you can access directly in Google Drive. And you can also follow it with the manual that we gave you. So today you are going to do inferencing on Haiti dataset that we put on the Google Drive. I hope you were able to download and or use it or to transfer it to Google Drive, your own Google Drives. And then this will be your next task in you can follow this with Kushanav. So for now, thank you so much for your attention. And if you have any questions, you can ask me on email, or you can also see my publications on ResearchGate, also some posts related to what we do on landslide detection, susceptibility, risk we follow, or we do a vast variety of topics at Machine Intelligence and Slope Stability Laboratory. You can also follow the link here. So now I give the stage to Kushanav. I hope if you had some questions, Kushanav was able to answer, because I don't want to waste more time at the moment. I will answer the questions when Kushanav is going to give the tutorial. I can answer some of your questions because we want to make you follow more hands-on session, because these kind of information of just theory you can find on internet, on YouTube, in about deep learning. So my main focus, I hope I was able to give you an overview of how we can use deep learning or machine learning for landslide detection in particular. Now, Kushanav, can you try to share your screen if you have access?
Yeah, let me try one sec. Yeah, can you see my screen?
Yes.
Okay,
Go ahead.
perfect. Yeah, just to say it outright, my Wi-Fi is not that good, so I'm just gonna show my face for now. Hello, everyone. Hope you guys are having a good morning or afternoon or evening, wherever you guys are. And okay, I'm gonna stop showing my camera for the moment. It's gonna be easy for the bandwidth that I have. Okay, so what I would like to start with first is going over the structures of the data sets that we have. But first of all, let's try to see where you can find this data, because I see a lot in the chat that some people are having difficulty finding, or at least accessing the Google Drive. So what I would like you to do is, when you get time later on, or even now, if you have the time, for today's for this session, please go to day 2, and then you'll find the second folder for deep learning, for landslide detection. And this is what you would ideally have, or you should ideally see in these subfolders as here. So what I am doing is, or what I did actually yesterday, was copy pasted all of these to my own private Google Drive, because well, there are 2 reasons. First reason is that I don't get privileges because it's from ITC, the accounts, I think, or outside my own administration. And second reason is that I think it makes more sense if I do it in my on my own personal drive, because at the end of the day, you'll be doing the same thing as well. So the folders and files would be pretty much exactly the same. Since I did it yesterday, I think the presentation of Sansar is missing on at my end, but I think it's still fine. All right, so we spent the last week trying to curate a code manual for you guys. So just in case if you had difficulty going through the presentation of Sansar, as well as what I'm going to present in a couple of minutes, you can always follow this code manual. So I'm not going to explain too much about this code manual because everything is here itself, but essentially there are 2 notebooks that that are important for you as a beginner, at least if you want to start diving into deep learning for landslide, or any other domain that you want to apply it on. So the most important notebook is the Landslide Automated Modeler notebook, and the second one is the custom data creation. The second notebook would be is provided in the appendix section, which is towards the end that you can see here. And this lines of codes, or this notebook, will allow you to create your own data set if you ever want to do it. Because what we'll be showing today would be data that we have curated before from our publication, which Sansar was showing a couple of minutes ago. The one then that he was talking about, the HRGLDD, the High Resolution Global Landslides database. So yeah, you can find all the information here. And today we'll be looking at a particular model, unit model, which is called the CNN model called the UNIT model, which was proposed by Rohnberger in 2016. I won't go much into the detail of this model per se, but just to give you an idea why this model is really good. One of the reasons is that it's an encoder-decoder structure, deep learning model that we're going to be using today. And what essentially does is that it allows us to give predictions for each pixel. So instead of having a prediction of, for example, you have an image, and instead of getting a prediction like, okay, there's a landslide here, what we would like to know is which of these pixels of that image has a landslide. So this sort of models help us to do that. And this sort of comes under the, let's say, concept of image segmentation. So it literally segments an image based on the pixels that the model thinks, or at least quote unquote thinks, because it's not really a human being, but that the model would probably think that it's a landslide pixel, right? So getting out of that, let's have a look at the structures of the folders. So you have the data folder, and mostly what we'll be using today is the arrays folder, because if inside the arrays folder, we have the data that we're going to be using from the HRGLDD paper that Sansar talked about again. And then these are data that we will be using to train the model, and then we'll be inferencing on, like Sansar said, on Haiti. So for example, Haiti is a data set that we didn't train the model on, so it's a completely new study area that the model has never seen, has never trained, and we really want to see how well the model performs, or just to get an idea of what the model thinks when it looks at new images. And that's at the end what we want naturally, right? Because when we have a model that's trained properly, we want to know if this model works or if it makes sense. So that's why in this folder, you can upload your own images that you want to test, not exactly test, but try to predict the landslide when you want to make your inventories for the landslides. The other folders for images, inventories, and masks are mostly used for the custom data creation notebook. And I think if we do have some time, I can show that quickly to you guys. But nonetheless, we spent quite a bit of time in the instruction manual, so it should not be that difficult if we don't get time, if I don't get time to really explain that. Then heading into results, I think this is pretty self-explanatory. There are 4 subfolders. So the weights basically will have the, let's say in this case, the memory of the model that it learned after training over a certain number of times. And then each of them can be used to, you can treat each of them as single models, let's say, as an output, and then you can use these to actually predict the landslides. But don't be too confused at the moment, because I'll be showing how it really works later on. So if you have any questions, you can kindly put them in the chat, but most likely I'll be addressing them anyway in the coming few minutes. Then you have the plots. So these plots would basically talk about the evolving losses of the training and validation data sets, as well as the accuracies that we monitor, which would seem like this. But these are the results which you will get later. So I'm not going to spend too much time here. And then finally, you're going to have a CSV file where you get all the results stored here. And that allows you to really gauge which combination of the model configuration really makes sense for us to use when we, at the end, want to predict landslides on. And then, yeah, predictions, I think that's pretty explanatory as well. These are the predictions that you're going to have at the end. And finally, let's go to the nitty-gritty part. We have 3 codes here. The first code is useful for the custom data creation, but since we'll be focusing on this in the beginning, let's start with this. Ideally, you should have this icon here that you see on the left, which signifies that it's going to directly open on Google Collaboratory. But if the icon is something like this that you see below, you can simply click, you can simply right click, go to open with, and you can do Google Collaboratory. And if by chance this is not there as well, you can go to plus connect more apps. It should take a couple of seconds. Yeah, you can search here for Collaboratory, and if you're lucky enough, you can find it in one of the placeholders here, and you can just quickly install it. And then, so that's what I'm going to do, and I'm going to go to Google Collaboratory. All right, so since I have this here now, so this is the notebook that what you're going to find. We put some links here for your reference. For example, the link to the preprint paper that you see here, and then the link to the data set actually that we curated.
Sorry to interrupt. Someone is asking to repeat the process of copying files in the user drive.
Yeah, sure, no worries. This is I would, to be honest, I would appreciate answering these questions a bit later, but just for this moment, I can do it quickly. You can suppose, assuming that this is the one from the that is disposable to you, the one that is provided by the organizers, you can simply just right click here and then download. It's as simple as that. And once you download them, you go to your own drive. For example, let me go to my own drive, and then you can make a new folder. And then you can, like, let's call it QWE for now. And then you can upload it here directly. So it's pretty simple like that. And you can access Google Collaboratory directly the way I showed you before. So it's not an issue, if that answers your question. Okay, where was I? Okay, so I was talking about the dataset itself. So these are the datasets that you can download directly, but we have already done it for you. Everything is there in this folder called arrays. So these are the exact same data, so you don't have to download separately. But if you ever think that your data has gone lost, you can follow this link. And the third link is basically our GitHub. So pretty much has the same information that we have in the first two links, but just to sort of shout out to our GitHub. Okay, let's begin with the notebook itself. What's important for you guys to understand is that you need to have a Google account. So by any chance, if you don't have a Google account, kindly install, make your own Google accounts. And then once you do that, you can log into your Google Drive via this link. And then after you've done this, you can pretty much follow what I mentioned previously, and that'll allow you to come back to this stage, particularly if you don't have it readily installed. So now let's move on to the next cell. So in this cell, what we do is, and again, I'm basically trying to, I'm under the assumption that some of you might not be aware of Google Collaboratory, some of you might not have coding experience. So bear with me if I'm explaining a bit too much for the ones who knows a bit of coding specific to Python or have worked around Google Collaboratory. But I think it's important that for the ones who don't know, it's important for them to really realize, at least to some level, what we're doing. So in this case, what we try to do is we try to drive, or let's say mount, our Google Drive that we have made to the session of Python, or let's say to the session of Google Collaboratory. And this allows you to actually access the data that you have in your own Google Drive from this session itself. So it's simple. You just click, once you click there, you're going to connect to your Google Drive. And then you're going to click on to your name. You just, once that's done, in a couple of seconds, you can test it actually if it worked or not. And I can show that to you once this finishes running. Okay, so you can test this by actually clicking here on Files and then Drive. Then you should see My Drive. If you see this, then that means all of your data that you have in your Google Drive can be seen from here. For example, remember, I had these 3 folders, so I can access them directly from here. So that's a really convenient way of really mounting your Google Drive into the session that you're using now. But do remember that if you turn off or if you disconnect your runtime, then you would have to reconnect again. But so it's not a big issue, but just remember that and for simplicity's sake. So moving on, we try to install certain packages which are not there inherently inside Google Colab. So for example, Rasterio, which we use for raster images, like TIFF images, GeoPandas that we use for polygons, for example, like shapefiles. These are not inherently installed, so we need to install them separately. And these are some auxiliary packages which I use for this notebook. So we're just going to install that using pip install, and this installs it directly. And for some of you who have already worked on Python, they might know how pip install works. So it's just pretty much the same drama. Excuse me. Okay, so now that this is installed, we're just basically going to import all of these libraries and packages. All right. So you see that the GPU is not installed here. So that's why I'm getting this prompt that please install GPU version of the TensorFlow. This is because you can choose to go to your runtime, change runtime type, and then choose the GPU. You are able to run deep learning models without using a GPU, but it'll be much, much slower. So it's better if you turn on your GPU and then start training your models. Otherwise, it's going to take the same time which it takes with the GPU, it's going to take longer time without the GPU. So a 5 minutes something could take around, let's say, 1 hour. Everything's installing again. Data system, it should be done as well. Okay, so 1 sec again. I think I have to reconnect again because I changed the GPU runtime. Sorry about that. All right, so since we have since we ran the GPU runtime, now we can see that we have selected a default GPU coming from the Google Collaboratory servers. All right. So next we're going to start loading the data. Remember when we talked about the data sets which were present in the arrays? So for some of you who don't know what's an array, it's basically a data structure where you can sort of look at it as containers where you can store your data. It doesn't necessarily have to be for image data. It can also be for tabular data as well. So you can store your data in arrays, let's say, for example. So since we had six sort of data for the training, testing, and validation sets, we basically use the same nomenclature, and then we try to assign the variables for that directly. And the important thing actually here is to understand what these numbers are, you know, and that's one of the reasons why I purposefully put this image here. So to try to understand it from a very elementary way, you cannot take an entire image to directly train it into a model. Like the model cannot accept an entire image directly. It's too huge. So what we try to do is that we try to cut it into small patches like this, or let's say grids. And that's what basically builds up to become these many numbers. So this essentially, if it was one big image, we made certain grids. And because of the number of grids that we have accumulated, that becomes this big number, for example. And then the next two numbers are essentially the width and height of each of these single patches. And then you have the number 4. And this number 4 refers to the number of channels or the number of bands that your remote sensing image has. For example, like Sansar mentioned, we were talking about planetscope images. So in this case, we have used red, green, blue, and near infrared. So we have 4 bands. So that's what you see here. And that's how we sort of divided the training data sets. So for the satellite image, we have 1,119 patches of size 120 by 128 and 4 bands. Similarly, you're going to have the same numbers for the label, because the label is a direct reference of the satellite image with association to the landslides itself. It might sound a bit confusing, but I'll explain much easily in the next cell, because I'm going to show you a figure of that. And it's one channel because it's basically black and white, or let's say in this case, it would be, sorry, I didn't run this. Okay.
Kushanov,
Yeah.
there is one question from Muhammad Abdel Hami. He's saying, I believe you need to make introduction for coding and the application. You just give them an overview what you are using here, like Python, and because some of them, they don't know what you are actually using here. Just give them an overview about just what programming language, or, you know,
Sorry, I didn't catch the question properly. Sorry.
No, it's just a question that they're asking you to make an introduction of the coding and the application that you are using. So this is also you are doing this in Jupyter Notebook in Google Colab, using Google Colab, and so you can just explain a little bit what platform it is, why you are using this.
Okay. So basically, the gist of why we're using Google Collaboratory. Well, the main reason is that it's free. For example, it's a platform that was sort of, let me remember, I think in 2017, this platform was created, which catered towards or let's say empowering or encouraging newcomers to artificial intelligence, machine learning, or deep learning enthusiasts, and for data-driven models. But the best thing about this is that one of the reasons why we use Google Collaboratory is because we have access to free GPUs up to a certain limits. But that's one of the reasons why we want to use, if you don't have a really chunky, heavy computer back home, if you don't have a graphics card, for example, it's difficult to even learn these kind of models because you would be sometimes disheartened because you can't really train really complicated models at one go. So Google Collaboratory really helps us redefine how we want to not really rely on really hardware that we need to buy, rather than using freely available resources that's provided by Google itself. If that answers the question. I'm sorry, I think that's what I got it from your question, to be honest.
It's okay, you can continue. Thank you.
Okay, no worries. Can we please keep the questions towards the end, if it's fine, Sansar?
Yes. No, it was just because some of them wants you to show something now so that they can follow. So it's just like that.
Okay, no worries. Where was I actually? Okay, I was here. So in this cell, we try to basically see what this data looks like. At the end, we talked about that these are data and arrays, but essentially this is what they look like. You have the satellite image patch of the size 128 by 128, and then you have the label, and these are the landslide polygons that we had initially, which we converted to images like here. And everything is there provided in the second notebook, and that's where you can do this kind of stuff directly. That will allow you to get the label or the ground truth images. So yeah, this is how we get the data itself. And then we go about to training the models actually, and then trying to look at the model training parameters. In this cell, we simply run the metrics. Metrics, quite easily defined, are the evaluation tools that we can use to see how well the model is performing over time. So it's just a measure of tool to use and trying to understand the predictive performance of the model itself. So in this case, we use precision, recall, and F-score or F1 score. This might get a bit technical in terms of explanation, but it's also important to understand why we use it. So just to give a quick understanding, a loss function is basically a function itself that helps us compare the values of the target, which is the ground truth that we have for the landslides, and the prediction values that comes from the model outputs. So essentially what you're doing is you're trying to measure if the models over time that they train, how much of this distance between the targets and the prediction values are. And the best scenario would be to minimize this loss values between the predicted and the target outputs. And so we want to get from here to the bottom. And this is done using very complex algorithms, but you don't have to worry about that. This code basically is written for someone who has no experience, but they can just simply run all the codes and input all the data, and then they're going to get the results directly. So here I'm initiating the loss function here. And then here, this is the most interesting part. So let's say the most important part, which is the point where we come to modeling. We have made effort to really explain what each of these lines of codes does. And unfortunately, since we don't have much time, I can't explain everything one line by line, but I'll try my best to explain at least the important ones that you can get away with, or at least take away from this tutorial. The size itself, this is quite self-explanatory. This size is talking about the path sizes, which is 128. So here we take a variable that we which is the X train that we got from the very beginning from the arrays, which is here, just to get the size. And this line of code basically tells us what's the number, and the number essentially is 128. Image bands, I think it's pretty self-explanatory as well. We take the fourth index, which is through here, this line of code, and this gives us the number 4, which is the number of bands. And then we define the loss function here as well again. Now, what's important next is to understand that training these kind of models is very, very complicated, because there are a plethora, like a lot of combinations of hyperparameters that you can use to actually get to a point of really training a good model at the end of the day. For example, you have hyperparameters like number of filters, you have learning rates, batch sizes, and there are even more. But what I'm trying to do here is show a very simple way of trying to look at some combinations, but then again, trying to get a realistic result towards the end that you can actually understand. So what we do here is we take a combination of certain filters, filter numbers here, but don't worry about it. This is not too important for you to really understand now. It's just to get an idea of how we would generally do it in our research, how we would train these models, for example. So we choose a combination of numbers for the filters. We choose combination of numbers for the learning rates, for the optimizers that we use, for example, and these are other hyperparameters. And then we do the same for the batch sizes again. And we have given comments here, which is going to help you as well once you start going ahead with your own training. And then one of the important ones is the epochs. This basically means the number of iterations that the model will train on. So how many times do you train your model? So epoch of 5 would mean you train your model 5 times. As a person who has been working on this for a couple of years, 5 is a very less number, and I think people who have done AI, at least deep learning, they would know that training 5 times is not that enough. It's not enough. But for the sake of the time, I'm just going to show you quickly with the 5 number epochs. But ideally, you should use something more like, I don't know, 200 or 300, or maybe even 700, 800 iterations, depending on the domain, the kind of data you have, and everything. But yeah, just to put it out there. And then here, what we do is that in these lines of code, we basically make, let's say, like a container, for example, like we make an empty dictionary where we fill in certain keys, and we want to fill up these values that we have used here inside these, so that we can monitor and track how the model is performing when we are trying to use these certain types of combinations. So the combinations would be basically like this. If you have these numbers, so it's going to be 4, this, and this. Then you train a model once, it's done. Second time of training, it'll be this, this, and this. And then that repeats basically. And then you're going to have like 90 combinations of model training. And then you have to choose the best one eventually. And that's what we do here with this nested for loop. So we loop over these various numbers that you see here. And then this is the entire model that you're going to be using to loop it over that you want to train it on. So this is the classic unit model of Rohnberger 2015. And so what do we do next? We look at initializing the model. So now we have made the structure of the model, let's say the skeleton of the model. Now we want to initialize this model. So we do that here. We initialize this model. This one could be a bit tricky to understand, but let me try it in a very simplistic way. When we train the model over time, you are going to get an increase in your performance. But if your performance doesn't increase after, let's say, a couple of epochs, it might mean that your model is overfitting. And what I mean by overfitting is that your model could be really good at predicting the training data sets or learning from the training data sets, but it will be really bad when it goes to some other places. So that's what we do here in early stopping. So you stop the model from training with, let's say, a patience of 30. So patience 30 means that if the model after 30 epochs doesn't improve, let's say, then you're going to stop the training of the model. And that's pretty much about it. And then what's next? Model checkpoints. In this case, you basically make checkpoints. And these checkpoints are essentially what you saw here. So when you train the model, after each iteration, you're going to get the weights here. So the weights are recorded because of this line of code here. It makes checkpoints where by monitoring the performance as well. And then here about you go actually train the model. So model.fit is the API that TensorFlow uses to train the model on. So to start training the model. And that's about it. So here you essentially start training the model, and until here, here you're basically trying to set the parameters and trying to set how the model would train, but you actually start training from this point onwards. And these lines of codes basically saves everything that the model will start once it starts learning and going forward. So all of these results would be saved inside the results folder here. For example, you see these are plots. So these plots would be saved in the folder called plots. So you can actually monitor how the model is performing. So for example, remember I told you the loss has to be low. So this loss value should keep on going down and down and down. So if you see that it's not going down, then that might be something wrong. And that's what we try to monitor with these plots here. And after this, we have a third type of data set, which is called a test data set, right? If you remember, we have training, validation, and testing. So testing data set is actually used to really check if the model performed well or not, because it's the unseen data sets that the model has never seen and never really have any idea about. So we want to see how do they perform there. And then what we do is that we load the model again in a new variable. Then we load the weight, which is this, for example. It's going to load the weight for that run of the model, and then it's going to evaluate on the X and the Y test. And it's going to tell you how well the model performed when it was compared to when it was compared to the labels of the Y test, which are the labels itself. And then once these are done, these are saved in a CSV file. And I think at the end, this is the most important one, because in the CSV file, you can actually see everything, all the model hyperparameter combinations and what sort of accuracies you get. And the key thing to remember is that since we use the metrics to determine how well the model is performing, it's good to look at, for example, the F1 score, which is one of the best metrics for image segmentation. You can look which number is the highest. Although these are 0.5, 0.6, but actually it should be read as 60% or 56% or 60% like this. So that's how you do this. Let me take something right off here, which I can see is the biggest one. 50, yeah, 50, it seems 64, 16, and 0.01. Okay. And once you start running this line of code, the model basically starts training here. So let me see if I can run this now, actually. Yep. So you see that the model is basically training now, essentially. So you finish one epoch, you finish two epoch, you finish three epoch. And then, yeah, this is your first model, which is done. It's finished, basically. And this model would be saved as a results in the results folder for the individual subfolders, actually. And then it's going to do it again and again and again for the variety of combinations that we mentioned here, for example. So all of these combinations, the permutation of these combinations comes out to be about 81 all the permutations add up to 81 combinations. So there'll be 81 times this model will be basically running. So it's running for the second time, you see here. I'm not going to do this for the entirety because it's going to take an entire hour. So I'm going to stop it right here. But all the results that you see are basically these. And I arbitrarily now I'm going to choose this one, for example, because I see that it's 64 seems to be one of the highest amongst from here. And then what I'm going to do is we're going to predict these landslides on the test set now. We evaluated the performance here by model eval. We got a metric that gave us 64%, and now we're going to see what it looks like actually. So simply what we're going to do is we're going to go to results, going to the weights, and then we're going to find the number actually, which gave us the how do you say this? The right weights which gave us the highest accuracy. For example, It was the one where we had 16 filters and 0.001 learning rates. So I remember that by looking at the CSV, so I'm not going to really find it here, but that's what you have to look. You go to the CSV, you find the right combination, then you find the combination number from here in this list. And then you take that one, you basically right click, rename, and you just copy paste this name here. And then you go back here and then you copy paste it here. I've done it already so that we can pretty much see it easily. And then you basically run this line of code, which are going to give you the predictions. Here I'm reporting just for the first 10 predictions, just to see what it looks like. Okay, doesn't look that bad, to be honest. So the first one is the satellite image. The second one is actually the predictions made by the model. And this is the ground truth, which is actually there in reality, or let's say the inventory that you have digitized yourself to compare it to. So it's not that bad, but I think it could be better, to be honest. But again, we have to remember, we only trained it with 5 epochs, so it's not too much. So you can see there are clear false over predictions, or let's say false predictions in this part that you see here. So these were not mapped as landslides, but these are apparently the model thinks that these are landslides. But if you train with more epochs, with more iterations, like 700, I don't know, 500, it might be possible that these, it would be possible that these would not be there after training for that many epochs. All right. So let's get about to the last part, which is actually looking at inferencing. So we know that we use this data sets, right? But this data set has no, it has been trained, let's say, for now, let's assume that this is a properly trained model in this case. Now we want to try to see how it works in a new landslide event that has occurred. So, and ideally that's the motive towards the end, because we want to see how well these models perform for real life applications. So we downloaded an image from Haiti, for which was affected by core-seismic landslides in 2021. I think it was in August, if I remember correctly. So that's what we do here. So this line of codes will basically import the image, which is Haiti. And remember, it was in the folder called inference inside data. So this lines of code basically does that. So it just loads the data. And then what we see is that the number of bands are 4 as well. So remember, this is quite important. That's the number of bands of the image that you want to predict on, which is this, has to be the same on the image that the model was trained on. So it's not like that you have trained your model on 4 bands, but you want to predict on an image of 5 bands. That's not going to work. So you have to be careful in this kind of nuances. And yeah. So now next, this is a long bit of code, but what it does, and I'm not going to spend time on explaining this, to be honest, but just on a gist, what this does is does the predictions by making these patches, which I showed you above. So the algorithm or that code line, those lines of codes will basically make these patches, and then is going to individually run predictions on each patches one by one, and then it's going to stitch it together. If you get what I'm trying to say. So that's what this line of code, and this was assisted by Ashok Dahal, who is going to be also presenting on Friday. So yeah. Okay, so now that we have these predictions made, you have to remember that these are still in the array formats, remember? So now we need to convert them to a format that we can actually use it in our GIS platforms, for example, be it QGIS, Saga, or ArcMap or ArcPro, for that matter. So that's what these two cells of codes does. It converts your predictions to TIFF images, so raster images, and Esri shapefiles. So you just have to assign the directory where you want to save it. So in my case, like I showed you previously, it was in the folder called predictions, where I want to save it as Haiti. So that's what I'm going to do here. So it's going to save it as a TIFF, and this is going to save it as a shapefile. So depending on how you want to use it, you can do it either way. And then let's try to visualize what these predictions look like. So let's first visualize the satellite image here. So here we're just trying to visualize the satellite image of Haiti that we know. So clearly, these looks like landslides here, here, and here. And let's see what the model has performed. And voila, you see these landslide as predictions that you see here. So all these blues are basically what the model thinks are predictions. I do have to mention that there could be some locations of false positives. For example, this could be areas where it's just a bare surface, a bare scarp of the mountain face, or let's say the hill face, and might not be actually slides, but could most probably be just the bare lands. But the model picked it up as landslides as well. But again, remember, we only trained it for 5 epochs. It's not ideal. If you train it with better epochs, with better configurations, you're going to get even better results. But yeah, that's I think that's what I want to show you in terms of like what we can get by having your own data sets and then trying to also predict it on instances where you have no idea how to get the landslide polygons. And then essentially these could become with proper training, these could become your landslide inventories that yesterday Hakan Tanyash as well as today Sansar was talking about, and also Afar when he was mentioning about trying to get to a point where we can get these polygons for the landslides that have occurred. So yep, I think that's what I had to present for today. I'm terribly sorry. I understand that this could be a bit too overwhelming because it's a lot of jargon. It's a lot of coding for those people who don't have experience. A lot of stuff could be confusing, but that's why we also made the instruction manual so that you can take your time really to digest what we have done here and then trying to really implement it yourself actually. So yeah, thank you.
Thank you, Krishna. Most of the questions, all of the questions actually were answered in the chat. So
okay,
I would ask you if it is possible to show them how they can create the data sets by themselves, because many of them want to know and also do it by themselves, because now you just show them how they can use HRGLDD data set, but you know, it's just for me, but also for everyone who is attending this, it would be like interesting to know how they can create their own data sets, because that would really help them to implement this workflow by themselves for any area around the world for their use case.
No problem. I think we have a couple of minutes. I can.
Yeah, we have some time. That's why.
Okay, no problem. Let's try this actually. Let me go here. Data. No, one sec. Codes. All right. So we have this, and then we do the same thing, right? We had this notebook, then we right click, then we go to Google Collaboratory. And you have the same structure as well. You have to mount your drive again. I hope you remember that, but if not, you can visit what I said before in the video that you'll have later on. Then we install certain libraries which are not present inherently in Google Collaboratory. All right. Okay, so before moving ahead with the next from these lines of code, I actually want to show you how you're supposed to prepare your data sets, at least your subfolders. Okay, so images are going to have your satellite image. That's pretty much it. Your images are going to have your satellite images. Your inventories are going to have the shapefiles of your landslides. Let's say let's try to think of it from a different perspective, because we're really always talking about landslides. Let's consider it's a flood problem. Consider that these are all flooded areas that are 2015, and these are images of satellite images of areas affected by the floods. All right. So what we do is it's pretty simple, because we with a colleague of ours from Brazil, he wrote a code that helped really do this much easily on the code rather than doing it on a GIS platform, which is a function called generate mask. So what this generate mask function does is essentially helps you create what I showed you here as this image directly. So you're going to have a background pixel with a landslide, or in this hypothetical case, a flood pixel. So what we do is simply we take the raster path, which is the raster path for the satellite image. So Nepal 2015 in this case, Then we take the shapefile path, which is the 2015, and that's the shapefile path. Then we want to store it somewhere, right? So we have a folder called masks. I can show you again here, masks. That's where we want to save it. And we just call it by a name. Ideally, by practice, what I like to do is keep the names of the masks similar to that of the satellite image. So that's easy to, because remember, these are two different folders, masks and images. So even if they have same names, it's not gonna be confusing because you're gonna relate it similarly. So Nepal 2015, which comes from raster, is a satellite image. Nepal 2015, which comes from masks, are the literal masks which you make from the shapefile. Okay, so that's what we do here basically. We run this algorithm and then you should get, and remember, you can always go back here. You can check it here directly, actually. Instead of going here all the time like I'm doing, you can always check from here. You go to My Drive, you can go to Columbia, you go to Data, then you go to Masks, and you have this here generated because of this function. All right. And this next few lines of codes is just to read the data, nothing too fancy here. The code might seem fancy, I don't know, but it's not too difficult to understand. These three cells just helps you read the data. So you see the collection of images available in the list are this. So, and this is the satellite image list that we're talking about. And the collection of labels that we just made is this. So the names are similar, but they're still different because they're being read from two different folders. And then this function, which is called the grid-wise sample function, essentially does what I was trying to explain to you here. So that function is going to make you these patches directly so that you don't have to really worry about like, how do you make these patches? Because that's what you need to train a model at the end of the day. So this function is essentially going to do that for you. So you define the function, you ready the function. And then here here this would be generally empty. So what you have to enter here are the names of the images. For example, let's say hypothetically you had two images, right? You had the flood image of 2015, you have the flood image of 2016. So what you would do is basically write this for at this moment. Let me just copy paste it here. You're gonna copy paste it here, and assuming let's say you had Nepal 2016 as well, so you would just write Nepal 2016. So it's going to use these two images. These two are the names at this moment, but it's going to use these two inside this algorithm to make the patches for these two images, Nepal 2015, Nepal 2016. And that's pretty much it. But since now we don't have 2016, I'm just trying to show you 2015 at this moment. So you do this, and then you're going to get your, you get 165 patches now. So before with the training, with the data that we have from HRGLDD, we had 1,119. But with Nepal 2015, this is just a sample image just to show you, you have 165. So essentially what it's going to be is like 165. And also here you have to set the patch size, which is the size of the height and width of the patches. So it's going to be 168, 128, 128, 4, because there are 4 bands. So this is what's going to be the output shape of these arrays. And then we want to have 3 types of data sets: the training, the testing, the training, the validation, and the testing. So that's what this code will do here. You can choose your own splitting, like this is 0.0, this is 0.33, which means 33% of the data would be split between the X-train and X-test. So you can choose your own numbers here, depending on how you want to split your data sets. But what it does is basically gives you the training, validation, and testing data sets. And then you want to save it, of course, because if you run it until here and then you don't save it, it's not going to be in your folders. So we run this, and then we save it inside the folder called arrays again. I just made a new folder called Nepal just because we're working with this data. So if I go to, where was it? Arrays, Nepal, which I made just now, and then you're going to find the new ones here. So what I can do now is actually I can use these directly inside here in the main here, and I can just replace these directly with the Nepal data and just start doing the same thing again. So essentially that's what you get. The point is to reach to a point where you can get the arrays of certain sizes or certain numbers, 1165 in this case, with the patch sizes and the batch number. This is for the satellite image. And then you want to have the same thing, 128, 128, comma 1 for the label image. And that's pretty much it. That's what you want at the end of the day as your data sets that you want to train and then test and then validate whatever you want. So you can split it accordingly with this, but as long as you have this curated data, you can do any sort of modeling with this kind of models. Yeah, does that is it
thank you so much, Kushanav. So I hope we answered all the questions from already in the chat. So this was for today, but I just take this opportunity just to show you something for just 2 minutes. So there is, can you see my screen? Kushanav?
Yeah, I can
possible to see. Okay.
Yes.
So I just take this opportunity to say that there is a PhD position in our group in Padua is available. Just for 1 minute, I want to say this will be mostly on the topic on advances in landslide mapping and monitoring, combining optical and SAR data using AI. And then this is a fully funded position for 3 years, and it will be supervised by Professor Filippo Catani, Mario Flores, myself, and Dr. Ascanio Rossi. And there is another position we have is a 3-year fixed term contract for assistant professor. So if any one of you are interested, you can follow the links here in my LinkedIn page, or you can go to Machine Intelligence and Slope Stability Laboratory LinkedIn page, and you can find the links already in my presentation. Otherwise, I can also share them in the chat. So I think this is all for today. Thank you so much for attending, and see a lot of participants. Thank you. And if you have any questions, we can you can write us in the email or in ResearchGate or LinkedIn, or there are many ways now to connect virtually from any part of the globe. So I think for now, yeah, I would say goodbye and have a nice evening or day ahead. I will see you tomorrow in tomorrow's presentation by Luigi. Thank you.
And great presentation. Thank you very much.
Okay, thank you so much. Then I will now end the presentation. Bye.
Thank you.